Range changes strategy. The Precision Strike Missile, or PrSM, is built to replace the Army Tactical Missile System, ATACMS, and extend the reach of ground-based strike platforms beyond 500 kilometers. That distance matters. Longer range shifts engagement zones. It forces adversaries to reposition command centers, air defenses, and logistics hubs farther from the front line. It compresses reaction time and expands strike options. But extending range is not simply about adding fuel. Missile design is a balance between propulsion, payload, and guidance. PrSM uses a solid rocket motor to accelerate rapidly after launch. Solid fuel provides reliability and fast response, but it limits throttle control. Once ignited, the burn profile is largely fixed. To reach beyond 500 kilometers, engineers must optimize burn efficiency and aerodynamic performance. That introduces the first constraint, mass. A missile's total mass includes fuel, structure, guidance systems, and warhead. Increase fuel for range, and payload mass must decrease. Increase payload, and range falls. This is the range-payload trade-off. PrSM is designed to fit inside existing HIMARS and MLRS launch systems, but with improved capacity. 2 PrSM missiles can fit in a launcher pod that previously carried 1 ATACMS round. That means size constraints are fixed. The missile must fit inside standardized launch containers. That dimensional limit forces internal optimization. Every centimeter matters. Guidance is the next constraint. Long-range precision demands advanced navigation systems. PrSM integrates modernized inertial navigation and satellite guidance to achieve high accuracy at extended distances, but satellite signals can be jammed. In contested environments, GPS denial becomes a real threat. That means the missile must maintain acceptable accuracy even with degraded signals. Inertial systems drift over time. The longer the flight, the greater the potential error accumulation. Engineers must balance cost, sensor precision, and survivability against electronic interference. Then comes aerodynamic stress. As the missile accelerates and travels at high speed, it experiences extreme thermal and structural loads. Air friction generates heat. Structural integrity must be maintained during boost and terminal phases. Weight reduction improves range but reduces structural margin. Reinforce the body too much and range drops. Everything is compromised. PrSM also introduces the possibility of future variants with enhanced seekers or different warhead configurations. That flexibility adds complexity to internal layout and system integration, and then there is mobility. The strength of PrSM is not just its range, it is its integration with mobile launch platforms like HIMARS. Mobility increases survivability. Launch systems can reposition quickly after firing, but mobility also constrains missile size and storage requirements. You cannot simply build a larger missile without redesigning the launcher ecosystem. The missile must remain compatible with existing transport, reload, and deployment logistics. Then comes cost scaling. Long-range precision munitions are not cheap. To be strategically meaningful, they must be produced in sufficient numbers. Manufacturing complexity and component availability affect how quickly inventories can grow. Advanced guidance electronics, hardened components, and solid rocket motors all contribute to production costs. The physical limits are clear. Increase range too far and payload shrinks. Increase payload and range drops. Improve guidance and cost rises. Harden against jamming and weight increases. The Precision Strike Missile represents a recalibration of that balance. It extends reach beyond legacy systems while remaining compatible with existing launch platforms. It compresses enemy response windows while preserving mobility, but it does not escape physics. Fuel mass, structural integrity, guidance accuracy, and dimensional constraints define its ceiling. Modern warfare increasingly depends on range and precision. PrSM does not eliminate defense systems, it shifts geometry. When strike platforms can reach beyond 500 kilometers from mobile launchers, the battlefield expands. Rear areas become exposed. Infrastructure becomes vulnerable at greater distances. But every additional kilometer demands internal sacrifice. Missile design is math under pressure, and PrSM sits at the intersection of range ambition and physical constraint, a system engineered not for infinite reach, but for optimized reach within the limits of fuel, structure, and guidance physics. Because in long-range strike, distance is power, but distance always has a cost.